G'day, my name is Brendan. Welcome to the present and future of computing performance. I've been working on back-end server performance for a long time, and I'm going to share where things currently are and my views on the future. As a disclaimer, these are my views and they aren't necessarily my employer's or USENIX. I'm also going to cover various interesting companies and products that I think help tell the story of where things are headed, but this is not an endorsement of them, and this talk is also not sponsored by anyone. The predictions I'm going to cover may also be wrong, but they will be thought-provoking. I'm going to cover 8 topics, and the slides are online, and you'll see they include many extra details as fine print that you can look up later if you like, and many references. So the first topic is CPU processors. The clock rate in early processors kept going up and up. It was amazing. Things became so much faster just by upgrading the CPUs. Where will it end? Well, we know where it ends, and that is practically servers nowadays are using around 3.5 gigahertz clocks, or even 2.5 gigahertz clocks. To illustrate this, I've shown the server processor examples I see on Amazon EC2 from 2009 to 2019, and you can see we've leveled off at 3.5 gigahertz. Now, there are some exceptions. There are some server processors in the 4 gigahertz, and also workstations do go higher. So there's one that's at 5.1 gigahertz. But what's happening is practically we're scaling horizontally instead of the clock rate. So we're adding more cores, more hardware threads, and also more server instances. That's putting more pressure on the CPU interconnect. The interconnect between 2007 and 17 has only increased 3-fold, whereas the core count has increased 6-fold. Memory buses also haven't increased as fast as the core count, and this has been described as the CPU memory gap. It's creating a growing problem where workloads become memory bound. And I've talked about this in the past. You might have seen CPU utilization is wrong because it is misleading. It's including so many memory stall cycles that it can become dominated by memory stall cycles. When you see 90% CPU, you think you're instruction bound, when in fact, a lot of the workloads I see is memory stall cycle bound. So that's so confusing, it's wrong. And memory needs to become faster because the CPU cores are scaling and making this problem worse. Also in CPU scaling lithography, this is how small the gates are printed on silicon. Next year, TSMC, the largest producer of silicon wafers, expects volume production of 3 nanometer. IBM has already built 2 nanometer. Wow, 2 nanometers. Where is this heading? Half a nanometer, a tenth of a nanometer. I actually had to look up the size of a silicon atom radius. It's 0.1 nanometer. So you might think there is an atomic limit here, but I'd also be a little bit worried if my transistor gates were made up of only 1 atom. What kind of tolerances would that CPU have? Now, so it turns out I don't need to be worried because this is all made up. Since 2010, the nanometer process should be considered a marketing term and no longer reflects reality. There's some new terms proposed that include GMT for gate pitch, metal pitch, and tiers, and LMC for logic memory and interconnects, and I hope you start seeing people use them. I've got a reference in the slide to explain how they work. And IBM's 2 nanometer CPU, just an example, had a 12 nanometer gate length. It is expected that the lithography limits, which are still improving, will hit a limit by 2029. Other ways to scale processors, including continuing to add special instructions that improve targeted workloads, like the AVX512 VNNI for machine learning workloads. There is connected chiplets where the chips are placed edge to edge and they have a high throughput bus. And 3D stacking that we're seeing more and more of in memory, storage, and we'll see that with CPUs as well. And there's already been a CPU using 3D stacking. Later server processor examples, I've just included some on this slide. This is the moment where if these seem way futuristic, then maybe it's time for you to upgrade. So we're hitting like 40 cores for Intel, 80 cores for ARM. That's really amazing. AMD has 64 cores and lots more LLC cache. Coming soon to a data center near you, hopefully, although there is a chip shortage that may last through to 2022 and 2023. But there's more chips to choose from. Amazon has led the way by developing a new CPU, Graviton, and they've got a new release, Graviton 2, based on ARM Neoverse N1. It's really impressive that a cloud vendor has now become a processor vendor, and not just created a processor, but one that's competitive and is in production. Microsoft have already announced that they'll do something based on ARM, and Google will have some systems on a chip thing coming out soon as well. At this point, I'd normally share Graviton 2 benchmark results. I think it's promising, but it's a lot of work to benchmark things properly and to make sure that we've tested it in production and we've understood all the differences. Accelerators, apart from more CPUs, there are now TPUs, FPGAs. These improve targeted workloads. GPUs have had widespread use for a while in machine learning. FPGAs are your reprogrammable semiconductors, and they're great for compression, cryptocurrency, video encoding, and certain algorithms. They are difficult to program. They require specialists to program. In the slides, I have a reference for the Microsoft FPGA-based configurable cloud, which is very interesting. They're doing a lot of things with FPGAs. And there's also TPUs, the Tensor Processing Units by Google. Make sure you're monitoring them. These are the other CPUs you may not be monitoring. To give you an idea of the latest GPUs, NVIDIA GeForce 10,000 CUDA cores, and Cerebras has an 850,000 AI-optimized core GPU. And they're using most of the silicon wafer for one chip that's the size of a dinner plate. And it uses 23 kilowatts. The previous generation was already the largest chip ever built. So it's a very interesting data point as a way to scale. The latest FPGA examples include almost 8 million logic cells from USENIX and 2.5. And the 2.5 version has been in production for a while in the AWS EC2 F1 instance type. We can have up to 8 of these and use them on demand. BPF that I'll talk about later has already been implemented in FPGAs. Now for my predictions about processor performance. I think in most cases, multi-socket is doomed. It will be an edge case technology only. And the reason is single socket is getting big enough. We're getting to 80, 100 cores on a single socket. Also, we're scaling horizontally on the cloud. So if I need more than 80 cores or 100 cores, if I needed 1,000 cores, I can spin up multiple instances. There would only be a narrow region in this pyramid diagram I've drawn where multi-socket might make sense, but the way single sockets are getting bigger and bigger, I have to question why pay the NUMA costs. And so what I'm talking about is when you have multi-socket, you have memory connected to a bus to each socket. If I'm a CPU and I need to talk to remote memory, I might have to hop over the interconnect in a CPU, and that adds latency. And there can also be overhead with things like cache coherency and sharing various other resource I/O buses. Now, I have to thank all the engineers that worked on this because it was an incredible amount of engineering to allow multi-socket to work in the first place, to get cache coherency to work in the first place, to have NUMA memory nodes in the kernel. And this served its role when applications could scale bigger than a single processor. But that role, I think, is in the past, and we now have single sockets that are just big enough to run applications, and when they get bigger, they split across a cloud service. I think there will be a more commonly used form of multi-socket, but that's when you have a core socket and a GPU socket and an FPGA socket. Simultaneous multi-threading or hardware threads, I think the future is unclear. Seeing these new ARM processors released with so many cores makes me a little envious because performance engineering on cores alone is so much easier than doing it with hardware threads where you have variation based on what the other thread is doing. Sometimes if I need clean benchmarks, I'll turn off the hardware threads. And some people turn it off for security reasons in the post-meltdown inspector world. So, future unclear. Core count limits. There is an 850,000 GPU, but imagine that for general purpose cores. I think there'll be a lot of problems with that. we're still scaling far beyond the memory buses can accommodate, and there's going to be massive kernel and app lock contention if we tried to go to 1 million general purpose cores, power consumption, false sharing, lots of worsening problems. I think there'll be a practical core limit for a given memory subsystem and kernel, and that may be something like 1,000 cores. Now, of course, with the exception of GPUs and machine learning, and they can keep scaling up. Apps themselves have a much smaller practical limit, depending on the app and how it does pools of threads. So I'd say there's 3 areas of processor scaling. The first is clock frequency that we've already reached, and then there will be a core and thread count limit that we may reach by the mid-2030s, say 1,000 cores. And then what are we going to do with the extra die space? Well, processors, the lithography will still shrink until the end of the 2020s, and we'll continue stacking layers of silicon. I think the next era will be improving the caches, the level 3 cache and its eviction policy, level 1 cache and level 2 cache. To go beyond is going to need very different technologies, like the use of graphene, carbon nanotubes, and so on. I've got a reference in the slides. There's also going to be more processor vendors licensed, and we'll have an era of CPU choice. Just beware of optimizing for the benchmark. I was thinking in these slides, I could show you how you could design a CPU that would benchmark really well. And I thought maybe I won't put a recipe to make it that easy. So production, these things have to be tested in production. It's a different workload than micro benchmarks can reveal. And I'm sure at some point there will be some CPUs that are optimized for the benchmark. Cloud CPUs, I think, are really interesting because they have an advantage. Large cloud vendors are running hundreds of thousands of customer workloads, and they can analyze them directly. This is going to give them a vast amount of real-world detail to aid processor design, so much they may need to use machine learning-aided processor design. I have an example that's the example screenshot shows Intel processor trace. It gives you time-stamped instructions. And so the next generation of CPUs based on analyzing so many workloads may see quite a significant production boost. It may not be so much in the micro benchmarks, but by analyzing the production workloads and optimizing for them is going to make a big difference. I'm really looking forward to people taking this on. FPGAs, I actually think there's going to be a turning point, and that's where a major app has support for it. And the JVM would be a very obvious candidate. Imagine you could apt-get install OpenJDK-21-FPGA, and that downloaded an FMI for the FPGA, and then you just had to run Java -XX plus use FPGA. Something like that will see major adoption. Maybe it's Java, maybe it's something else for FPGAs. Memory. Many workloads I see nowadays are memory bound. And here's some screenshots of one of my tools, PMC Arch. IPC's instructions per cycle. IPC of 0.1 is really bad, so that's lots of memory stalls. Even IPC 0.6 is also bad. Instructions per cycle for production workloads can get to around 1.5. And so when I see 0.6, I see we have at least 2x headroom on the table if we improve our memory subsystem. DDR5 is coming out this year and will help. It has better bandwidth. It does need processor support. Intel Sapphire Rapids supports it. And it's already DIMMs. Samsung has a 0.5 terabyte DDR5 DIMM. And so you can see on the graph, bandwidth is improving with each of these DDR releases. What about latency? Here I've plotted DDR from the year 2000 had a latency, single access read latency of 15 nanoseconds. And that actually hasn't changed, surprisingly. The reason is internal to the DRAM, the memory clock, 200 Hertz, hasn't really changed. And I saw a great talk by Mark Greenberg who described it as a cost function. This is optimal for DRAM, and while they can make it faster, they think they're serving customers well by leaving it at that. And so that's why we see latencies that are all very similar. Low latency DDR does exist, reduced latency DRAM by Infineon and Micron. I haven't seen widespread use. It has very low density, like a gigabyte DIMMs. I've seen it marketed towards high frequency traders. But maybe it's not DDR that's going to see Big changes in memory. It's HBM, high bandwidth memory. This has already been in use on GPUs, and it uses 3D stacking to scale. And the Intel Sapphire Rapids processor has been rumored to include 64 gigabytes of HBM on package. That's really interesting because it'll herald a new era for memory, where we don't need to have external DIMMs. We have enough memory to run applications right on the CPU package for enterprise, for server, for cloud use. And it'll be high bandwidth memory as well. It may not be lower latency than DRAM. I haven't seen enough latency numbers to understand that. The size of server DRAM is also scaling. And I've got an example here from Supermicro. 4 terabytes of DDR4 can go on this system board using 16 DIMMs. I'm only showing you the single socket configuration and not the multi-socket configuration because I said earlier, I don't believe in multi-socket generally going forward. This is great, but I also like to look at the Open Compute project because they have more balanced configurations, balancing the CPU count and the memory count so that it fits applications. And so that example, 1 socket, 96 gigs of DDR4. So yes, you can scale up on single socket if you need to. That doesn't mean you have to because you might find a more optimal balanced configuration. Another interesting development for memory is the addition of a new tier of memory using 3D crosspoint below DRAM. And 3D crosspoint I'll cover in the next section. It can operate in different modes. And the idea here is it improves performance. Instead of going to the storage devices, it can go to persistent memory and be 10 times or 100 times faster. Predictions: DDR will keep doubling its bandwidth every 8 to 10 years. I mean, I am assuming miraculous engineering work, and this is not a JEDEC announcement. But will single access latency drop in DDR6? I guess not, because it seems they have already found what they think is their sweet spot, and low latency is left for other memory technologies. DDR5 will still be exciting because double the bandwidth. For some workloads, you will have up to 2x wins. HBM-only servers I would predict they would happen as well. And I can imagine a cloud offering high bandwidth memory, HBM-only instances, no external DRAM, super fast memory. And this is going to help CPUs close the memory core gap or memory CPU gap. Also, we may see RLDRAM as another option. If we're going to stack HBM on a processor, why not stack RLDRAM so we have a low latency memory option as well as this high bandwidth memory option? And the extra tier I mentioned, I think it's too late to be where it is. So it would have made more sense a while ago, and I appreciate the engineers making it as an option. It's not the only option for 3D crosspoint. It has more compelling uses in the next section. But main memory in the meantime has become so massive, it can fit the working set size of my applications comfortably. And so by the time, like we're in terabytes of DRAM now, by the time I'm falling out of main memory, we're talking super cold data, like ice cold, absolute zero cold data that's very infrequently used in general. By the way, in general, I've written some tools to do working set size estimation and analyzed this before. So improving the speed of that very cold data, making it 10 times faster, I don't think is going to generally make a big difference. Disks. Here's a recent timeline for rotational disks. And technologies like perpendicular magnetic recording and multi-actuator recording, which has more than one arm, they will improve performance. Shingle magnetic recording we're starting to see a lot of that. That does not improve performance. The last two, I don't know their performance characteristics yet. They're very new. Things like heat-assisted magnetic recording that uses a laser to warm up the disk. Shingle magnetic recording, so what happens is the write head, the way the magnetic fields work, is larger than the read head. And so the write head writes in an overlapped fashion, knowing that the read head is effectively smaller and can read the unoverlapped data, thus increasing density, 11 to 25%. Improved storage, bad for performance, because if I overwrite something, I have to I have to rewrite the overwritten tracks. So this is suited for archival or write-once workloads. When you're purchasing disks, just check if they're SMR and see if that matches the workload you have in mind. Flash memory-based disks have gone through many technologies as well, from single-level cell, multi-level cell, and so on. The more levels they add, the worse the block array cycles. So we're now up to quad-level cell, which is only rated for 1,000 block array cycles. 3D NAND, or vertical NAND, is very interesting. This is where multiple layers of flash memory are stacked, and SK Hynix can see 600-layer 3D NAND in the future, which should be in the multi-terabyte range. SSDs, as a performance engineer, they're super fast compared to disks, but they do have their own performance pathologies because they have the flash translation layer, they have latency from aging, wear leveling, fragmentation, internal compression, and so on. This is my diagram of how 3D XPoint works. So you have word lines, you have memory cells, and they're accessed via a word line and a bit line will identify that particular memory cell. That's how DRAM works. What's different about 3D XPoint is these are then stacked vertically. And so word lines and bit lines have memory cells on both sides. And so this increases density. So DRAM, this is trapped electrons and a capacitor requires refreshing. 3D XPoint, it's stacked. And it also is a different technology. It's a resistance change, which makes it persistent. It's really exciting because it has low and consistent latency. And as a latest storage device example, this was released as I was developing the slides. Intel Optane memory has 512 gigabytes of QLC NAND, and then has 32 gigabyte or 1 terabyte, and then has 32 gigabytes of 3D XPoint as an accelerator. And now currently that's for laptops, but we'll see that for server storage as well. Storage interconnects are also getting much faster. So, and I've got tables here showing the SAS and PCIe bandwidth is improving. NVMe 1.4 is the latest. And also, these newer specifications do have features other than speed, like reliability and power management and virtualization support. Apart from hardware and software, for storage, Linux has the Kyber IO scheduler, and Netflix is using that and seeing up to 300 times lower 99th percentile latencies. And that was added in Linux 4.12. Some predictions. I expect slower rotational disks because they're going to focus on what they're good at, which is archival workloads, more weird pathologies, so bigger, slower, and weirder. 3D XPoint, I think, is going to be great as a rotational disk accelerator, not just a flash memory disk accelerator. I haven't seen the rotational disk accelerator version yet, but also as massive storage because it can keep stacking as petabyte storage. And more flash pathologies. As flash gets bigger, I expect to see worse internal lifetime, more wear leveling and logic, and more latency outliers. So bigger, faster, and weirder. And I'd love more observability of flash drive internals to help me understand and debug them. Networking. The latest hardware, 400 gigabit is in use, 800 gigabit is next. And it's not just about speed. There are NIC features as well that are important, like inline TLS or TLS offload to the NIC. Protocols, QUIC is seeing more and more usage. That's TCP sessions over UDP, which is faster. And MPTCP for multi-path TCP to improve performance. So these are some of the latest protocols that people are adopting. Linux has some new TCP congestion control algorithms. So Netflix is using TCP BBR, and on a 0% packet loss network, it doesn't make a difference. But when you have packet loss, like 1% packet loss, Netflix sees 3 times better throughput. The Linux network stack has lots of moving parts. It's getting more complicated. I drew this diagram for my Systems Performance 2nd edition book, and it shows that these are the areas to tune, queues and tuning. And the send path, more and more features keep getting added. So we've got pacing, TCP send offload, congestion controls, NAGL, TCP small queues, queuing disciplines, generic send offload, and by-queue limits. So as a performance engineer, this is a lot of work for me because I need to make sure these are all working and tuned. But overall, it does improve performance. Software, XDP is something new for networking, and that uses eBPF or BPF as a programmable fast lane in the kernel. The next plenary session is on XDP programs. My prediction for networking, BPF in FPGAs, and there's already been some examples of that, because they have massive I/O transceiver capabilities, so we'll see great I/O-based applications moving into BPF. Cheap BPF routers using commodity hardware, which is kind of the use case of where eBPF came from in the beginning as software-defined networking. There's going to be lots more demand for network performance because apps increasingly network. Netflix has 4K content, and there's also lots more remote work and video conferencing. So more demand for network performance engineers. Runtimes. The latest Java at Netflix uses a lot of Java, so I wanted to talk about that. Java 11 has many smaller features, but I've highlighted things like the low latency garbage collector, GZC, and the low overhead heap profiling, and GC adaptive thread scaling. Java 17 is going to be released soon, September, and that can make better use of vector instructions, has parallel GC improvements, and lots of other perf improvements. One I'm particularly interested in is the JMH JDK benchmarks that are included in Java 11, and that gives us a standard suite from which to measure Java performance. My predictions for runtimes, FPGA as a compiler target, I already mentioned that. I/O U-ring I'll mention soon, and that's to accelerate I/O-bound workloads. That's a new Linux kernel technology. I'd also like to see more adaptive runtime internals. There's so many options between GCs and compilers and this and that for the runtime to try them multiple options in parallel and then choose the best. And also, as we scale up processors, we need better runtimes, libraries, and programming models to help programmers write code that scales to that many cores. Kernels. This is the latest kernels, FreeBSD 13, Linux 5.12. 5.13 is in development. Some Linux performance features. I/O U-ring and BPF are some of the big ticket items. I/O U-ring is faster system calls using shared ring buffers. And so instead of doing a synchronous system call and waiting for the return, it can queue many in a send ring buffer, and those system calls complete on a completion ring buffer. It allows I/O to be batched and to be asynchronous. Runtimes and libraries need to support I/O U-ring, and we should see great performance improvements for I/O-bound workloads. eBPF everywhere. That's another kernel feature, and I've got a screenshot of the Microsoft open source blog. Microsoft are working on bringing eBPF to Windows, and they've got an open source version that's showing that work. Great to see. And I should mention eBPF is the same thing as BPF. So kernel engineers and myself, we tend to say BPF, but we mean eBPF, the extended technology that's now just BPF. In the future, BPF, which is a technology, it's a generic execution environment in the kernel. It allows applications to be written in user space and then run in kernel mode, but in a sandbox, so it's safe. So it's not like writing kernel modules that can panic your system and may have security vulnerabilities. This is a much more safer and practical way to write those sort of specialized applications. Maybe they're networking things, security things, performance things. I write a lot of performance tools in BPF. There was a prediction from Stephen Restet, who's the perf maintainer and also the real-time patch set maintainer. BPF will replace Linux. There's so much excitement about what BPF is doing. I mean, it's basically doing to the Linux kernel what JavaScript did to websites. It allowed us to do so many new things. Emerging BPF users, observability agents, security agents, there's already TCP congestion control algorithms can be done, and even kernel drivers. My prediction, future BPF users, more policies in the kernel can be implemented in BPF, like file system buffering and read ahead, CPU scheduler policies, and so on, so that we can customize them for different workloads safely. And also lightweight IO-bound applications like proxies could be written in eBPF entirely. Another prediction for kernels is I think they really need to become jittered. So for a while, you can do PGO or auto FDO for kernels so that you take the performance information and then recompile the kernel based on that performance information. So it can do better branch prediction, it can do better instruction locality, and so on. But it's a lot of steps. It's hard. The kernel needs to do this by itself. It needs to just work. I think kernel emulation will still often be slow, and that's where people are running, having a syscall layer so that you can run one kernel apps under a different kernel. And the problem is the syscall layers don't expose everything. There's a lot of things that aren't supported, and they return E not supported. OS performance, very, very interesting. Linux is great. I mean, it's everywhere. Lots of performance features, but I worry about its increasing complexity and worse performance defaults. And it's getting to the point where you do need an operating systems team to be working on it to make it perform well. And I worry about the defaults rotting, because those that do have performance teams, like for example, Netflix always puts down its own tuning when it deploys a base AMI. So Netflix doesn't have a clear picture of what the untuned Linux or the default Linux performance is. So we may see rot in the defaults just because we don't have enough of the high performance engineers taking a look. And that may make more room for a lightweight kernel that's easy to tune and stay on top of the defaults like BSD. And BSD, Netflix is still using BSD because for that workload, the Open Connect Appliance, the CDN, it is faster than Linux. I helped analyze the last production test. And so BPF will find its high performance for narrow uses. And Windows, I expect it to see performance improvements because of eBPF and the observability it provides. Unikernels, I think, will get one compelling published use case, and that will be it. Hypervisors. Containers are being rolled out everywhere. Secret v2 support is improving the hierarchy of how those resource controls work. Container schedulers are being adopted, Kubernetes, OpenStack, and more. Netflix has one it develops called Titus. And there'll be price performance gains by Tetris packing workloads. Performance tools, many of them are still not container aware, so they don't work so well when you try and run advanced things inside a container. More work needs to be done. Hardware hypervisors. So Amazon has released the Nitro hardware hypervisor, which cuts the number of steps between the guest operating system and Metal to improve performance. And I drew this diagram to show how the near Metal performance has been taking over all the different workload attributes, like using SRIOV for networking and storage, and the culmination to be the AWS Nitro hardware-assisted hypervisor. You may have heard me talk about virtual machines many years ago. I talked about them and talked about the value of Solaris zones or containers versus virtual machines, and how it's so much better to be running zones. But the industry has changed, so these virtual machines are now much faster today because of all of this work. And there's a new type of virtual machines called lightweight virtual machines that can boot super fast, similar to a container. For example, AWS's Firecracker. That has benefits because you have your own separate kernel inside the guest, so all of your performance tools should work. So my prediction, those performance tools to fully work inside containers is going to take several years. In the short term, we will see containers everywhere, but I think in the long term, we'll have more containers than VMs because they're great for light to medium-sized workloads, but then your really high-performing workload application, lightweight VMs have a number of advantages to give it a dedicated kernel. So you're not sharing kernel resources. You don't have the seccomp overhead, the overlay overhead, full perf tool access. You can do PGO. And so I think with lightweight VMs for those, just the highest few workloads only, they will also use a lot of CPUs based on their workload. And this is the evolution. So functions as a service for very light workloads, then to containers, lightweight VMs, and then metal if needed. Not all apps are heavy, so they don't have to make it to the end of metal. So this is as appropriate for the workload. And for cloud computing, I see microservice IPC costs drives need for, we're seeing container schedulers co-locating chatty services to improve performance, and also BPF-based accelerators to improve the container networking like Cilium. And cloud-wide runtime schedulers, I'd like to see them co-locate apps in the future. Imagine multiple apps under one JVM roof, and the cloud-wide runtime scheduler manages that. There's already technologies to do that inside the JVM, but we need a scheduler for it. And the final topic is observability. At USENIX LISA 2010, I gave a plenary on I gave a talk on heat maps. It was on visualizations. And now latency heat maps are everywhere. At USENIX LISA 2013, I gave a plenary on flame graphs. And when they were new, and so it was very important to help adoption, flame graphs are now everywhere. 2016, I talked about BPF, and that's now everywhere. We're heading everywhere. So USENIX LISA has been very helpful for distributing these ideas about upcoming observability technologies. And so I'm very grateful and thanks for everyone involved for continuing to run it and for you for continuing to attend it. Now, observability, it also has changed. And personally, I joined Netflix in 2014. And when I began working on Linux, on EC2, there was no dtrace and no PMCs. And so nowadays, I would say it's the age of seeing, because we have BPF and BPF trace, advanced traces, and we have PMCs in the cloud with Nitro, so I can look at low-level CPU performance. So nowadays, if you can understand anything if you need to. Here's a diagram. I'm showing all of the different BPF performance tools and what they instrument. In red are the new ones I developed for the BPF Performance Tools book. They're all open source, so you can use them. And if you haven't seen a BPF tool by now, here's an example BPF tool. ExecSnoop is just logging commands, super useful for finding out what's running that you may not be aware of. There's a BPF trace one-liner for doing a frequency count of the block IO type. And a new technology for BPF is libbpf. It uses compile once run anywhere core and BTF, BPF type format, so we can have these standalone binaries that include the relocatable BPF bytecode. And so there we go. OpenSnoop stripped is only 151 kilobytes, and it contains everything. A modern observability stack, OpenTelemetry, Prometheus, and Grafana are also very important these days. Predictions. BPF tool front ends, it's BPF trace and libbpf tools. There are many at the moment, but these are the ones that are going forward. I guess I'm cheating a bit of this prediction because I'm influencing this myself as an engineer. I do think in the future we'll have too many BPF tools, and I'm partly to blame because I've been developing them. And it's a good problem to have, but in 2014 I had no tools to work on various things I needed. And by 2024, I know I'm going to have too many tools for this problem. I think the solution there is GUIs. We need GUIs to help people find the tools and execute them more quickly. That's an example BPF GUI that my colleague Susie is working on at Netflix. And another one, Flamescope adoption. USENIX, I was talking about flame graphs in 2013, and then now I keep seeing them rolled out in new observability tools and products. The next problem you're going to see with flame graphs is that by default, they're not good at looking at variance and perturbations because they're showing a 30-second summary or 60-second summary. And that's why I developed a flame scope with Martin Spear at Netflix, and that shows you using a sub-second offset heat map the variance and perturbations. You can see it visually, you can select a range, and it gives you a flame graph just for that range. So that would be my prediction for the future. So to recap, I covered 8 topics, and performance engineering is actually getting more complex. So I've done performance engineering for a long time. There wasn't this many things to get one's head around, but that's the nature of technology. It is difficult, but it's been my pleasure to summarize a lot of them here for you. And you'll find if you want more information on a particular technology, I have the many references in the slides that will be online. And thank you very much. I will be online to answer questions, and please discuss my predictions and share predictions of your own. And it'll be interesting to see what people have to say.